Consider the factorial. It is often defined in terms of repeated multiplication, as seen here. For n equals 100, that amounts to 99 mathematical operations. In previous lessons, we have obtained 100 factorial by adding up logarithms. This would also require 99 mathematical operations. Today we are going to develop an approximation to the factorial function that involves far fewer operations, which means it can be computed much more quickly. To start, we must take a look at the function y equals the natural log of x. That is seen here, plotted from 1 to 10. Our objective is to integrate this function. That means finding the area beneath the curve, as seen in red. We can start by adding up a bunch of rectangles. This tends to overestimate the true area beneath the curve. As a sum, we can write it like so. A sub u is greater than the definite integral of the natural log of x from 1 to 10. In case you were curious, I chose the subscript u for upper, but it doesn't matter too much what I call it, so long as I'm consistent with my terminology. More generally, a sub u is greater than the definite integral of the natural log of x from 1 to any positive integer n. On the other hand, we could add up a bunch of rectangles like the ones seen here. This approach tends to underestimate the true area beneath the curve. The sum for a sub L is written like so. It is less than the definite integral. The subscript L stands for lower, but once again, the terminology doesn't matter too much. More generally, a sub L is less than the definite integral of the natural log of x from 1 to any positive number n. A sub u is greater than the definite integral, and a sub L is less than it. What if we average the two, as seen here? Now the approximation much more closely represents the true area. Effectively, this is equivalent to employing the trapezoid method. This was covered more extensively in my lessons on numerical integration. I just mention it here in passing. So let's see what happens when we take the average of the two, as just suggested. Adding a sub u to a sub L and then dividing by 2 gives us the expression in the last line. Just note that the trapezoid method would have given us the exact same result. Remember that the natural log of 1 is 0, so that first term disappears. What we are left with is boxed in green. This is important. We will use it in the very near future, so don't forget. We have seen in other lessons that taking the logarithm of n factorial converts a multiplication problem into one of addition. That is a direct application of the laws of logarithms. Here the example is shown for n equals 10. The same idea can be generalized to any positive integer n. Once again, note that the natural log of 1 is 0, so that term goes away. We are left with the result in the last line. This is also a very important expression to remember. The first two lines on this page are results we just derived. If we put them together, we end up with the expression boxed in blue. This is going to take us one step closer to the finish line. In order to get to the finish line, we are going to need integration by parts. That is boxed in orange. Above it is a simple derivation that many calculus students fail to appreciate. Consider two functions u and v. Apply the product rule of differentiation. Integrate both sides. Then rearrange. Pause the video if you need time to digest. Otherwise, accept the result boxed in orange as truth, because it is time to move on and apply it. We must use integration by parts to integrate the natural log of x. The process is shown in color coordination. Our final result is seen in the last line. X times the natural log of x minus x. Next, we must evaluate that at the lower and upper endpoints, 1 and n. The natural log of 1 is 0, so that term disappears. Our final result for the definite integral is n natural log of n minus n plus 1. Back to this expression now. I have substituted the evaluation of the definite integral, which we just did on the last page. That is underlined in blue. Simplifying things a bit, we get the expression boxed in purple. Here we do a bit of algebraic manipulation. To get n factorial, we must exponentiate both sides. A bit more algebra gives us the expression boxed in red. This is it. We have reached the finish line. This is an expression we can use to approximate the factorial of a number. So let's do an example with n equals 100. At first glance, it may seem like 36.7879 to the 100 requires 99 repeated multiplications. This is a bad approach. Elsewhere, we have seen how this can be reduced to 8 multiplications. Then multiply that by e and the square root of 100. Our final answer is on the bottom of the page. Instead of performing 99 multiplications to compute the factorial, we can get away with 10. That is a much more efficient approach. The downside to that, however, is a loss in accuracy. Our approximation tends to exceed the true value of the factorial by about 8%. That comes from the ratio 0.92. Divide n factorial by the approximation to get the ratio. The good news is, there are ways to improve our approximations and still get away with rapid calculation. I'm just going to put this here for now. In the next lesson, we will see that the square root of 2 pi is a better multiple than e in this application. Notice that the ratio is 0.92. That is very close to what we saw in the table on the last page. Where does the square root of 2 pi come from? Stay tuned for my next lesson to find out.